Hey guys, hope you're doing well. I'm excited to try this out with you guys. It's definitely going to be the most uncomfortable I've been in a while, especially since my sister is right there listening to me, so that's weird. She has her headphones on, so hopefully she's not judging me too much. Don't turn your volume on. Keep your volume on. Can you hear what I'm saying? Okay, perfect. Okay, so we're learning about exponential applications, which is really great because it goes right along with what we're learning in the world right now. So before we start, what I want you to do is go ahead and open up on your browser. Just go to Desmos. And then you're going to go to the graphing calculator. So you can look at some of this stuff. Alright, so just have that up on the side. It's going to be helpful as we're trying to calculate some of these values. Okay, so first let's get through some definitions. Alright, so when we have an exponential function, f, with a base b, we've seen a similar function before, but it's going to be f of x equals a sub 0 b to the x, or equal to a sub 0 b to the t minus t naught. Hopefully you can see that. That's a 0. I'm having a hard time making my thing small enough because I only have these big markers. Okay, so we already know that b is a positive constant other than 1, and a sub 0 is the initial value. We're in exponential growth when b is greater than 1, and we're in decay when b is between 0 and 1. Alright, we're going to start looking at equations where our b value is going to be equal to e. So we're going to have our b value as e. So these are, e is a constant. Well, first of all, b is the natural base. We'll just go through here. So e is the natural base. E is irrational. Where's that music coming from? Someone's singing Grace Potter on the television. Sorry, distracted. My roommate's watching American Idol in the living room. Okay, can I? Nope, can't pause this. Alright, so then E is about 2.71828, and it goes on forever because it's irrational. Alright, and we call E Euler's number or Napier's constant. This guy right here is Euler. Not that it matters, but it's kind of fun. Good looking guy. Okay, and so then just again, just want to say that E is the natural base. So that right there is important. All right, we're going to do a couple applications of this. All right, let me fix my camera so we can see a little better, maybe. Okay, there we go. All right, so coronavirus is real. It is following an exponential curve. Actually, I had the exponential curve up. I took it down. But someone basically calculated that 1.565 e to the 0.112x is the growth rate, or I'm sorry, is the exponential equation of growth for coronavirus. The growth rate is that 1.112 that we see right here in the equation, and that's an exponent there. So we're just going to calculate what each of these values are going to be. But first, let's look at the graph of this, we've got 1.565e to the 0.12x. Okay, so move my head over here. We can see that if we zoom out, this is growing exponentially. So this is apparently what it looks like. I don't think that's super accurate, but we're just going to use that information for problems because it's relevant right now. So we'll pull this back up here. There we go. We're going to calculate these values. So it asks what, so the functions for the number of people infected with coronavirus, and it's asking what will the number of people be infected be on day 10. So that's telling us that x is going to be equal to 10, and so we'll plug that in to this equation. So we'll have A is our population equals 1.565 e to the, I hope you didn't hear that noise, e to the 0.112 times x, which is 10. All right, so that's an exponent there. It's not very big. Can't really tell too much, but it is an exponent. Having trouble writing with those big markers. So, all right, let's go ahead, go over to our graph. Everything we're gonna do is we're just gonna type it in. I'm lazy, so I'm gonna copy this down and paste it, and then just plug in my value for x right here, which is 10. So at the end of day 10, there are 4.79 people infected. I'm getting a FaceTime call. Are you kidding me? What else could go wrong? Okay. Then this is about 4.79, but we can't have a partial person, so we're just going to say about 5 people are infected at the end of day 10, which isn't that many. Good stuff. All right, but after 3 weeks, I realized I didn't put it back to the screen. Okay, so we've got about 5 people are infected, but it asks how many people will be infected after 3 weeks. So we have to think about it. There are 7 days in a week, so we're going to do 7 times 3. So that's about 21 days is equal to x. So we'll plug 21 in for, gosh, I'm getting all these calls. 21 in for x. So it'll be A equals 1.565 times e to the 0.112 times 21. All right, so we'll go ahead and plug that into our calculator here. I'm lazy. I'm just going to change this 10 to a 21. All right, so at the end of day 21, there will be 16.44 people, which is about 16 people infected. That sounded so rude when I told my roommate not to come in. Oops. Okay. Where's the visualizer? All right. So that's about 16 people. All right. And then at the end of 2 months, let's go ahead and calculate that out. So there are about 30 days in a month. We'll say 31. We'll stick with 30. 30 days, multiply it by 2, because there's 2 months. So we have 60 days, which is about how many days we have now. So we'll test the validity of this here. Okay, so we'll do 1.565 times e to the 0.